All right, now we're talking about symmetry and the different types of symmetry to identify, and that can also help us in calculus. So the graph can be folded along a line so that the two halves match. A reflection, right? So when you look at here, in terms of the types of symmetry, the x-axis, here, this is considered line symmetry, or an axis symmetry. Or you can have a point symmetry, like with the origin. So the x-axis and y-axis are common lines of symmetry. The origin is a common point of symmetry as well. So we talked about all three. The following graph and algebraic tests can be used to determine if the graph of relations is symmetric to the xy or origin. So for every point xy in the graph, the point x negative y is also on the graph if it's symmetric to the x-axis. So you can replace y with negative y and you end up with the same result. For every point, this is with symmetry with the y-axis, for every point xy in the graph, the point xy becomes negative xy. So replacing x with negative x results in the same equation. For every point xy in the graph for the origin, well, this one changes both, negative x and negative y. So replacing negative y with negative y and x with negative x results in equivalent equations. So use the graph to determine if the relation is symmetric to the x, y, or origin, and confirm your answer by doing it algebraically. So you can see which axes would you fold over, and they would be one on top of the other. So this one has reflection over the y-axis. If you replace the x with negative x and then do the algebra, you would notice that the exponents that are even means that it would stay the same. So one of the ways to determine if something is reflecting over the y-axis is to look at the exponents. And if the exponents are even, it has symmetry with the y-axis. Alright, so this is x times y equals 6. We could also write this as y equals 6 divided by x. It's a rational function. Does this have symmetry? And you can tell it's not an axis, but it's actually over the origin. And if you replace x with negative x and y with negative y, you can see that when you multiply them together, it equals exactly what it was before. Number 3, what symmetry is here? This one actually has two symmetries. So you have the x, well, not the y, because the y then would have it on the right side. So just the x going down. And to prove it, you could take this y and make it negative, and you could see negative y squared means positive y squared. They're equivalent. That's what gives you the reflection. Here you can see you're reflecting over both axes, and if you look carefully, you're actually also reflecting over the origin. All of it. This is called a hyperbola. Y squared minus x squared equals 1. You could prove it in different ways. If you put in a negative y, it would become positive. If you put in a negative x, it would become positive. And if you change negative and negative, they both become positive. So you can see algebraically, I'm not going to show all three ways, that it has symmetry all three ways. Here, where does this have symmetry? So this one, number 5, you can't fold it over any axes. And the origin doesn't work either in terms of that. I mean, you can always take a point if you can find it, and then if you change to negative negative, it needs to match exactly. Number 6, which way does it reflect? So not over the x, but over the y. Absolute value. So for the y, if you take out the x and put in negative x for x, the absolute value of negative x is just x. So you can see that it matches what it is before. You can do this algebraically. You can also do it with a point. If you take a point on one side, to see that it matches the point on the other side. All right, even and odd function. So we talked, this is going to connect with symmetry. So a function is considered to be even if it is symmetric with the y-axis. So this is this idea, a parabola is the ultimate example of that, but if you have an even exponent on x, it will reflect over the y-axis, and we call that even with the even exponents. A function is considered to be odd if it is symmetric with the origin. So algebraically, if you plug in negative x, you get the same answer as you did before. Here, if you plug in negative x, you'd actually get a negative answer. It would be the opposite answer for whatever y is. So there's the algebraic test. You can also test a point sometimes as a quick way to check. So determine algebraically if it is. So the first thing I actually look at are the exponents, and because the exponents are odd, I say they're odd, right? So that makes it simple. Algebraically, if I plug in an answer like 2, and you get 8 take away 2 is 6, if I plug in negative 2, I should get the exact opposite answer. So this is negative 8 plus 2. So can you see the answers are opposites? That's a way to informally check that it's odd. Here, I see an even exponent, and then I see 6. Now in this case, think of x to the 0, and for these rules, 0 is thought of as an even thought in terms of it. So negative x squared plus 6, think of that exponent 0 as being part of the even family. This is even. If you plug in like 1 and get the answer 5, if you plug in negative 1, you get the same answer because negative 1 squared keeps negative 1 plus 6 is 5. Number 9. This is a jambalaya right here. So number 9, we'd say none. I don't need to do any testing. I have odd and even ones jumbled together. That means there's no symmetry in terms of odd or even. Square root again. If I look really carefully, but it's the square root of x squared subtract 4. So when I think of the exponent in terms of different things like that, what's going to happen here? I see an even exponent. If I replace negative x with positive x, I'd get the same equation. So it's a composite function where you have a parabola and a square root together in terms of what it would look like. Be intrigued, right, to see what it should look like a line if you actually graphed it. But it's symmetric, but it's a special kind of line it would look like. But we call this even, and that's that even exponent that you see there. You definitely have a domain restriction. You couldn't plug in any number. If you plug in a number between negative 2 and positive 2, you're going to get a negative answer. So everything's like greater than 2 and less than negative 2. All right, number 11, what do I see there? So what exponent do you see on the x? It's an invisible 1. It's definitely odd. If I plug in a negative number or a positive number, so if I say, hey, plug in positive 2, you get negative 8 divided by 2. That's negative 4. If I plug in negative 2, it should be the opposite answer. So negative 8 divided by negative 2 gives you positive 4. So there's an informal way to understand odd and even. Number 12, absolute value, positive 1. So it's shifted over. It does have an odd exponent, but it's that 1 that's not. Remember, the constant is considered an even. So when you have that odd exponent with that odd in there, right beside it, there's a jambalaya there. So this is neither even or odd. If you graphed it, it would be shifted 1 to the left, and so you can see that that's an awful looking. There's your little absolute value v. There's no symmetry over the axes or over the origin when you see that because of that plus 1. The absolute value of x without plus 1, that would have symmetry on the y-axis and be considered even though it has an odd exponent because of the reflection of it. All right, to the page. Here's one again where I'll just go right into the homework in terms of, I just call it just a practice sheet. Practice the lesson. So here's an opportunity for you to do the work and then see if it matches or not. So you try it, and if you're right, you're right. If not, listen to the video and maybe I can give you insight of which way it is. So, is this odd or even? So I see that exponent. It already gives me that sense, right, that it's odd, which means it's reflecting over the origin. If I get this and I look at the picture, I can see that again it's reflecting over the origin. And you can see the odd exponent there on x. Here, when you have an absolute value, it's not even about the exponent, it's just the reflection over. You can see it's around the y-axis when we reflect that. Here, when I look at it, there is none. So if I reflect over, they don't go on top of each other, either axis or the origin. Here, which axes would you fold over? So one would be on top of the other. So you can see it is the x-axis. Here we have a circle. Well, circle's great. The x, the y, the origin, it's symmetry everywhere. Over, like go across the x-axis, across the y. The origin, it has symmetry all over the place. The beautiful circle. All right, turn the page. Can you determine if something's odd or even, and how efficiently can you determine if it's odd or even? So I see even exponents, so I can see it's even. I see an odd exponent, and it's a line, so I know it's odd. Here, the square root of x, or the other one had the x squared. Well, that's great. If I do an informal test, so if I plug in like 5, so the square root of 5 minus 4, that's 1. If I plug in negative 5, it should give me the opposite answer. But if I plug in negative 5, you get negative 5 and negative 4, and negative, it's imaginary, so it doesn't exist. If this was an odd function, then this answer would have been negative 1. 10, the absolute value of 5x, and then subtract 6. That's that absolute value bar, so we're not worried about the exponent as much. You can even think of the v going down. So whatever I plug in, whether it's a positive number or a negative number, the answer will always be the same, and subtract 6. So this is an even function. Having an idea of the graph where it goes down 6 and it's really skinny looking, kind of that's that v, a skinny looking v, that's what the 5 does. And it goes down 6, and there's that reflection over the y-axis. Here are two odd exponents, so I clearly see it's odd. Here we have a jambalaya, so it's neither. Gonna get hungry if you talk about jambalaya. All right, number 13. Here we have the absolute value, but because the subtract 9 is inside, it shifts it to the left or right away from the axes. This is neither. There's no symmetry there. Here, the cube root of 5x might be helpful to know what the the picture of it, in that it doesn't move away from the origin. So that 5 makes it a little skinnier looking, but we have this kind of thing where over the origin we have a reflection. If I plug in a number that's positive, or if it's negative, you get the idea that they're opposites in terms of it. So 5 is not a nice number to try to figure out cube root with. Cube root is what number 3 times itself. You know, if this answer inside was 8 or 27 or 81 or something like that. But when you see the graph and it stayed at the origin, you can see the reflection over the origin. So number 14 is a odd reflection. All right, so great lesson, good thing on odd and even and symmetry.